Okay guys, so let's discuss now some extended principles on torsion, and this is applicable uh, specifically on I-shaped sections, but can actually be further extended to other shapes for as long as the intention is uh, find is based on the principles mentioned here in this discussion. Okay, so we have learned about the pure torsion proposed by Saint Pinat, which is more applicable on circular shaft. This actually ignores or neglects warping because for the Saint Venant torsion, the formula is simply an application of the GJ theta, uh, which defines your torsional curvature in terms of the moment. So where theta is actually the rate of twist as defined on our uh, lecture on torsion, can be represented by the derivative d phi over dx. Okay, so this is actually the rate of twist theta, and this is known as the torsional curvature relation. Okay, where G is simply the modulus of elasticity for shear, and J is the polar moment of inertia, which is actually a torsional property of the member. For warping torsion, we can actually make an analogy to I-shaped sections by simply um, considering an equivalent system for the I-shape, upon which your moment, the torsional moment induced by the force P with an eccentricity E, can actually be converted into two horizontal forces, or simply coupled to formulate some equations applicable to I sections. But this can further be extended to channel sections, because we know for a fact that a channel section has also two flanges, wherein your force pH can actually be concentrated. So it won't affect any assumptions which were used on the formulation of our torsional derivations. Take note that the torsional moment is reckoned from the shear center, not the centroid of your section, which happens to be of the same position and location when we talk of doubly symmetric shapes like the I section. So this is again a representation on how the flanges, particularly the compression flanges, uh, are affected by the twisting moment um, in a direction which is lateral or sideways. Okay, so if I consider now this flange element with your axis, no? So this is now the centroid of the flange element, wherein at the ends twisting is prevented. So the axis, regional axis now, due to the torsional moment MZ, may cause the flange center line to buckle or to bend, no? Sideways. Uh, in that observation, we can come up with uh, with an analogy of taking into consideration a lateral bending instead of a pure torsional behavior. Okay, so in this case, a displacement equivalent to UF, signifying the flange, no, the flange deflection or displacement. UF is actually going to the right, no, as this whole shape actually rotates clockwise in this direction. So UF there can actually be a representation of the UF here, considering the torsional behavior, while here we are actually considering a sideway deflection or a lateral bending, okay, which will is categorized on the lateral torsional behavior concepts that we are going to discuss for the rest of this lecture. So from that figure, we can now define some equations. Let's say, say the displacement of a point at the flange as a function of the angle of twist phi. Okay, so the angle of twist phi is defines simply your u displacement by multiplying it to the distance, now which is measured from the neutral axis uh, to the extreme fiber h over 2. Okay, so consequently, if I differentiate this flange displacement 3 times, I will obtain a third derivative of UF equivalent to the third derivative of phi with respect to z multiplied by a constant h over 2, and we consider this as your equation 1. Okay, for uh, the interpretation of a simple beam bending or beam curvature, we can now recall the moment curvature formula, wherein the second derivative of the deflection or displacement, UF in this case, is simply your curvature MF over EI. Okay, so where the F here, the F's actually indicate the flange element as your member for which the beam curvature is actually obtained. So differentiating it with respect to z in this case, okay. So one more time, differentiating it with z, since your variable of consideration a while ago is the z variable, we obtain the third derivative as of UF equivalent to the first derivative of the moment curvature parameter MF over EIF. Taking note that the derivative of a moment with respect to an axis, a coordinate axis, say z, is simply your shear. Okay, so take note that the derivative with respect to any coordinate axis of a moment is defined as your shear. Okay, so this formula here now, this third derivative here, is also equivalent to the shear on the flange divided by the sectional property EIF. And substituting it in equation 1, we may now mix up the two equations and finally come up with the formula for your shear at the flange equivalent to the negative EIF h over 2 d cube over dc cube phi, okay, or the third derivative of phi with respect to dc. So we now define warping torsion MW as the one that makes your flanges move laterally opposite with one another. Okay, so we have seen in our first figure here that the moment brought about by an eccentric load can actually be transformed into an equivalent system wherein this moment PE represents the couple pH. Okay, and therefore if we try to look at the shear, okay, so if we represent this pH as your shear force, okay, so this is now assumed to be your shear force at the flange BF. This couple now will represent the warping torsional moment that will cause these flanges to buckle, or sorry, to displace sideways, therefore exhibiting a behavior known as the lateral torsional buckling, and that warping moment can now be expressed as equivalent to BF times H, and substituting the value of BF here in this recently derived equation, we can come up with this formula here where your H over 2 becomes now H squared over 2 because of the additional moment arm H that exists on the formula for your warping moment or warping torsion. And if we let this whole parameter, okay, separating your modulus of elasticity from this inertial property, we can now describe this as your warping torsional constant CW, upon which your values on the roll shapes sections as introduced on the AISC table was obtained. Okay, so CW is simply equal to IFH squared over 2. And finally, the simplification of such will yield to your warping moment equivalent to the negative ECW third derivative of your phi with respect to z. Okay, so phi here is again the angle of twist. It is not the curvature that we are using, okay, in flexural behavior. So this is not the curvature, but rather it is the angle of twist. So the torsional moment now of the whole uh, section is simply a sum of the rotational part and the lateral bending part. This rotational part being your pure torsion given by the St. Venant torsional concept, and your lateral bending part is actually the warping torsion discussed here in this lecture. Okay, so ms plus mw is simply equal to the total moment. So if we can actually make an analogy of a simple shear diagram equivalent to the torsional diagram of a beam loaded by a constant uh, torsional moment at the midspan. Okay, so if I have a beam here, okay, which is simply supported, and I apply a twisting, okay, so I apply a torque here at the midspan, say T, my torsional shear diagram will simply be equal to T over 2 there and negative T over 2 here, okay? So this will be your uh, total torsional moment T equivalent to your total moment, say. But again, this total torsion, or this total torsional moment, is a sum of the pure torsion and the warping torsion. So this can actually be decomposed into a St. Venant torsion like this. Okay, so this is now your pure torsion plus okay, a warping torsion like this. So if I add these two here, so the shaded parts are the values of the torsional moment. So it will end up into this simple torsional shear diagram. Okay, it's just like a shear diagram. Okay, uh, represented by the shaded area. So take note of that, class, no? And we take note that the St. Venant torsion is simply a GJ theta. Okay, simply GJ dphi over dc, where this is again equal to the rate of twist, and MW, or the warping torsion, is simply equivalent to the one we have derived a while ago. Okay, so ECW d cube over dc cube phi. Okay, so you might be wondering why there's a negative sign here. So I'd like to emphasize that the negative sign here uh, sometimes is confusing, only indicates okay, that your relation on the bending lateral, so this is a lateral bending, simply indicates that your direction, which is your z direction, is opposite, no? It's opposite the convention used for positive bending, which is upward. Okay, so if you still if you notice on your beam curvature, your phi is actually m over ei, but m here is actually indicates your displacement, which is downward. Okay, so later on you will notice that this negative sign will still uh, will go back to an additive value uh, to compensate for the confusion it caused in this particular derivation. No? So if I were to derive this, I will not use a negative sign on it. But I followed the book of Salmon and Johnson. So and I uh, assume or presume that simply this is an indication of the right hand coordinate system that are used when we do some computational programs, and it simply boils down to uh, retaining it back into its original uh, convention later. Okay, so if we rewrite now and divide by ECW this equation, you will notice that I moved this on the other side, I moved this on the other side. So this will be your equation. Okay, so I just jumbled it now. So third derivative of phi minus jg d phi dz is equal to the negative of mz, and I divide it by ECW. So the Bob equation is a non-homogeneous equation, therefore it requires a sum of a homogeneous solution and a particular solution. So what makes it a non-homogeneous? Because your right hand side is not zero. Okay, so in your advanced math, this is elementary procedures on how to deal with a non-homogeneous equation. You set this to zero first and then come up with a parameter lambda squared to substitute your coefficient of your variable of consideration, which is phi, and therefore this is now uh, phi triple prime. Okay, you can say phi triple prime minus lambda squared is equal to 0. Okay, so this is a simple characteristic equation, and the solution has the form ae to the mz. Okay, and this is the one that I'm talking about. So this becomes m cubed minus lambda squared. There's a phi here. Okay, lambda squared m is equal to 0. So we cannot make this to be 0 because you will have a non-trivial solution, or a trivial solution rather. So we equate this to 0 because this is not 0, and therefore the above equation requires that we simply make use of factoring, factor out m. So our roots will be 3 roots because this is in the cubic equation. So we have m equals 0 and m equals positive and negative lambda. So substituting it back to the original equation AEMZ. So we have now phi h is equal to A1E to the lambda z plus A2E to the negative lambda z plus A3E to the 0. So there's an E to the 0 here, but E to the 0 is simply equal to 1. And your coefficients A1 and A2 and A3 may now be determined uh, by substituting boundary conditions later. Okay, so note that lambda, as I have defined it here above, is simply jg over ECW square root, and I come up with another variable to represent lambda, which is 1 over a. And for the particular solution, since mz is in general some function of z alone, the form of the solution may be written directly as mz is a function of z. And what does that mean? So we just look into the original differential equation, and we take note that these are constant. Therefore, the right hand side of the equation has the form of a solution equivalent to the function of z as described by mz. Okay, so mz is simply a function of z, therefore theta p is simply a function of z. Adding the two solutions, we come up with this, okay, uh, differential equation in the third degree or third order. So okay, so we just substitute it back to the original equation, where the terms on the left hand side must be paired with the terms on the right side, and rarely will the function of f1z be required to contain higher second degree terms. So this is now your final differential equation that will represent your torsional behavior for I sections. Thank you very much, and I'll see you on the next video to continue some more derivations of the formula that will serve as basis for our lateral torsional buckling solutions.